Greetings everyone. We are Team 14 and our project focuses on enhancing the design for manufacturing and assembly of an autonomous food delivery car. Our team comprises of Aryan, Dhyan, myself Devang, Rahul, Sarvesh and Siddhartha. Our chosen product is an autonomous car designed primarily for food delivery purposes. To provide context, the average production of such cars in North America amounts to 1.2 million units annually, generating an impressive $590 million in revenue each year. Our presentation begins with an overview of a proposed CAD design of the autonomous car, followed by an exploded view showcasing each component essentials for its assembly. Key components highlighted include the battery, motor, wheels, ECU, front filler, back filler, motor mounts, and container. Also, the container is being enclosed by the cover. The primary customers identified for our autonomous vehicle is the food delivery services, and secondary customers are the remote exploration researchers. In the fast diagram analysis, the primary function of our product is food delivery. Therefore, the primary branch encompasses the fundamental aspects of a food delivery system, including acquiring and transporting food and confirming delivery and payment. To determine the priority for redesign, we employed a quad chart analysis. Utilizing this chart, we will make informed decisions regarding the elimination and redesign of selected parts to optimize our RC vehicle design. Following the fast analysis of our product, we have created a matrix correlating components with functions they perform. This matrix serves to illustrate the crucial role each components play in fulfilling the functions of our product. Remarkably, every component is associated with at least one function, indicating the importance of each element in the overall functionality of the autonomous car. This following matrix underscores the diversity of functions performed by the product, catering to both primary and secondary customers. By describing the functions unique to each customer group, we gain valuable insights into tailoring our product to meet diverse customer needs effectively. Additionally, we have developed a component commonality table, segregating modules responsible for different functions from components that remain consistent across various product variants. As we delve into our project, it's essential to note that we are focusing on two distinct variants of autonomous vehicles. These variants necessitate tailored designs to meet specific functional requirements. The primary differentiating factor between the variant lies in components ranging from the ECU to handle. Given the weight function of each vehicle type, it follows that ECUs will differ between the two variants. Additionally, distinct battery requirements are anticipated, along with adjustments to overall external packaging to accommodate these differences effectively. Specifically using the product family design, we intend to incorporate a camera module in place of a handle. This modification aligns with our goal of enhancing functionality while maintaining efficiency in design. By introducing these changes strategically and delayed differentiation among the components of the primary and secondary customers, we aim to achieve the desired mushroom shape in our project progression.
Coming to the design for assembly, we determined the theoretical minimum number of paths to be 13. Each path's assembly time was calculated individually and summed up, resulting in a total assembly time of 171.52 seconds and an assembly efficiency of 22.73%. Following an in-depth examination of assembly cost and the quad chart, we opted to focus our DFA efforts on two key sub-assemblies, the cover, which is a module, and the wheel hub, which is a platform. These selections were made based on their significant assembly costs and higher functional importance within the overall system. When addressing the cover sub-assembly, we applied 4 DFA guidelines, namely DFA1 reduce part count, DFA2 reduce fasteners, DFA4 allow hand and tool access, and DFA7 add features to facilitate orientation. The initial illustration presents two distinct components, the cover and the handle. The subsequent figure demonstrates the revised consolidated part resulting from our DFA enhancements. Now, in order to optimize the wheel hub subassembly, we employed 3 DFA guidelines, namely DFA1 reduce part count, DFA7 add features to facilitate orientation, and DFA11 providing locating features. The initial figure represents individual components such as the motor mount, motor, fasteners, hub, and wheel. These elements were streamlined into a single part as illustrated in the subsequent figure. Here we calculate the change in the DFA manual assembly time after implementation of the before discussed changes. The process still remains the same. Each part's assembly time was calculated individually and summed up. Now we can see a significant decrease in the total assembly time, which went from 171.52 seconds initially to a mere 80.15 seconds. The theoretical minimum number of parts also decreased to 9. The assembly efficiency though jumps by 48% from a 22.73% magnitude to 33.68%.
Hello everyone, this is Dhyan Vyas and I will talk about the DFA automated assembly analysis. The sub-assembly of container, front and back filler is chosen as the motor and motor mount sub-assembly was eliminated during the DFA manual assembly analysis. As is clear from the quad chart, the container falls under high importance, high cost section and is a justifiable choice for DFA automated analysis. Front and back filler although have a low cost, but given the high functional importance, reducing its cost furthermore will have the evident impact on the cost and operation of the part as a whole. This is the DFA automated analysis for the selected three sub-assembly components. Given that the container design has minimal areas of optimization, the focus of optimizing the design from the assembly standpoint and reducing the sub-assembly cost is front and back filler. The slide shows the optimized front and back filler design based on the DFA guidelines that helps us reduce the part variety and amount of fasteners. This also eliminates the possibilities of tangling and nesting of the part on the feeder. The modified features are highlighted in red and blue. The design changes in the container are kept to a minimum, but still the amount of fasteners are reduced and the hand and tool access inside the container is improved by elimination of the hinge and incorporation of vacuum seal between the lid and the container. The reanalysis shows a reduction of approximately 16% in the sub-assembly cost by changing the designs of the container and front and back filler.
Hello everyone, I'm Siddhartha and I'm going to talk about process selection. Process selection helps us in choosing a process which minimizes the cost of the production by considering various specifications such as material, shape, mass, section thickness, tolerances, and the production batch size that we are planning for our product. We can choose the perfect process for our part. We take into account the process capability attributes and finalize the candidate processes. We use multiple charts to eliminate the processes that are incompatible at various stages. We have chosen container and filler to go ahead with process selection. You can see the specifications of each part on the screen such as weight, maximum wall thickness, tolerance, and surface roughness. Over here, we can see the particular stage at which each process fails. As we can see, for container, sheet forming and machining are the only processes that qualify, and for filler, machining and injection molding are the only processes that qualify.
Hello everyone, I'm Rahul and now I'll explain about the DfM process that we followed. So here is the first component that we chose for post DfM analysis. So this is a front and back filler of our vehicle, and here, as you can see on the left side of the slide, we have computed cost of the component from analytical method, and it was around 12 cents. But then we utilized DfM Pro as well as the rules taught in the class, and we redesigned the component using DfM rules. And basically we implemented three rules. The first one was we reduced the wall thickness, and we reduced the maximum wall thickness from 16 mm to 2 mm in the redesigned component. Also we made the wall thickness uniform across the component as 2 mm, and also we provided 2 mm 5-degree draft angles everywhere in the product. And because of this redesign, we got almost 50% reduction in cost, and also we maintained all the function of this component as before. This slide shows before and after DfM Pro screenshots from the software. The second component that we chose for DfM analysis was the container, and this component was already redesigned after DFA, and after DFA we figured out that this component is already optimized for sheet metal, and using DfM Pro we did not find any recommendations from this for this component, and so we kept the component as same as before, and the cost of this component was $11.77, as well as we maintained all the functions for this component.
Hello everyone, my name is Sarvesh. Next up is product service systems. We are offering two distinct services. Firstly, food delivery services. Here, autonomous food delivery vehicles are provided to services like DoorDash, which are seamlessly integrated into food delivery ecosystem. These vehicles autonomously navigate urban landscapes for prompt deliveries, showcasing economic design and capabilities. The second is remote exploration. Here, our vehicles are tailored for autonomous surveillance operations, equipped with navigating autonomously while collecting valuable data for researchers. This service highlights innovative product design and functionality. Now on to the environmental impact. Currently, the surge in delivery activities and vehicles is driving up the greenhouse gas emissions. To address this challenge, we propose experimenting with autonomous vehicles to cut labor cost, ease traffic congestion, and ultimately curb emissions. While automation alone may not directly reduce carbon emissions, transitioning to electric delivery vehicles can make substantial difference. Moreover, these are added benefits like efficiency gains and shorter delivery times. With this, we end our presentation. Thank you for your attention.